This is ELC 131, Circuit Analysis 1, and we're going to talk about the DC equivalent of an AC sinusoidal voltage source. Now, I've sketched a sine wave on the board, and this sine wave has a peak value of 10 volts and, of course, a negative peak value of negative 10 volts. And I show that AC sinusoidal source connected to an incandescent lamp. And that incandescent lamp has a resistance of 10 ohms. Now, during the first positive half cycle of this AC waveform, from here to here, this voltage source is positive to negative. Current will be flowing in this direction through the lamp, and as current flows through the lamp, the filament will heat up and generate light. Now, during the second half cycle, when the polarity changes to negative to positive, now current's going to flow this way through the lamp. And since current's flowing the opposite direction through the filament will actually suck light out of space back into the filament because, of course, current's going the opposite direction. What? You mean it doesn't work like that? Oh, man. Let's start over again. So, during the first half cycle, when the voltage source is positive to negative, we'll have current flowing around in this direction. And of course, the current will follow this same sinusoidal waveform. It'll just have a maximum value of 1 amp. And the power dissipated in that lamp is going to go up here to 10 watts. Now, during the second half cycle, or the negative half cycle, the voltage is now negative to positive. Current will be flowing in this direction, and the current is going to be negative 1 amp. However, it doesn't matter what direction the current flows and what the polarity of the voltage is, power dissipation is always a positive value. So I guess the question is, if I want to get the same amount of light out of this bulb with a DC voltage source, what would be the value of this DC voltage source? Would it be 10 volts? Would it be 5 volts? What would be required for this DC voltage? Now, what we have to do is think about the power dissipated in this bulb. And note, looking at the sketch, the power starts at 0. It goes up to 10 watts. It goes back to 0. It goes up to 10 watts. It goes back to 0. But in order to determine the average power, what we have to do is actually find the square of the voltage. After I've found the square of the voltage, I have to find then the average power throughout this entire cycle. And because I squared everything earlier, what I need to then do is find the square root of the average over one whole period. So when we talk about effective DC voltages, we talk about the root mean square, or RMS, value of a sinusoidal waveform. This term mean comes from statistics, where we find the average of a value or a series of values. So the root mean square of an AC sine wave is the DC equivalent. We will express this as V sub RMS, which means the root mean square value of a sinusoidal or an AC waveform. Now, we'll quite often, instead of writing VRMS, simply express this as VAC, all in capital letters. So VAC means the same as VRMS, which means what is the DC equivalent voltage to this AC waveform. And mathematically, the RMS value equals the peak value times 0.707. So for our example, with a peak value of 10 volts, we would get the same light out of that lamp with a DC voltage of 7.07 volts. Again, a 10 volt peak sine wave creates as much light and heat, or power if you will, in a load as would a 7.07 volt DC source. Now, we can look at this in the opposite direction and say, what is the peak value when given the RMS quantity? And for example, in our homes, our voltage is 120 volts AC. So what is the peak value of the sine wave that is provided to our lights and small appliances? Well, V peak would equal what? VRMS divided by 0.707. So 120 volts divided by 0.707 gives us 169.8 volts. I think that's right. So in your homes, at the receptacles and provided to your lights, we have an AC waveform that goes up to 170 volts down to negative 170 volts, back up to positive 170 volts, all at a frequency of 60 hertz. So in your homes, if you could view the waveform at the receptacles or at the lights, this waveform would go up to 170 volts, down to negative 170 volts, and that all happens in a period of 16.67 milliseconds. So when we talk about AC waveforms, we can talk about these waveforms in terms of their peak value, their negative peak value, or we can talk about them or quantify them in terms of their DC equivalent voltage value, which is the root mean square of that AC waveform. It's expressed as either VRMS or VAC. And for sinusoidal waveforms, our conversion factors are that VRMS equals V peak times 0.707. And of course, the peak value equals VRMS divided by 0.707.